problem is it takes like.
I/O talks have too many hybrids.
Was it like the lower bound, or like no? The lower bound is nothing. Like the only conductive part is the LW construction, right?
Yeah, so it must be the LW construction.
Or is it? No, it maybe not. But like then like it's one run. Yeah.
I don't remember. It's been like a year.
Okay,
But I promise I still care.
Okay,
I haven't forgotten.
No, it's just like that.
Yeah, no, I agree.
All right, so yeah, very happy that Omer Paneth decided to take a very expensive flight from Israel and come give a talk about batch arguments and applications.
How do you know? Okay, so hi, thanks everyone. So my name is Omer. I'm going to talk about batch arguments, or BARGs for short. So we've been talking a lot about SNARGs in this workshop, and in the past 5 years or so, we had really great progress on building all kinds of SNARKs based on standard assumptions. So I've been sleeping really well. And I don't know, to me, maybe the main character in the story is this notion of batch arguments. So this talk is going to be just a tutorial. I'm going to mention some new results, but mostly I'm going to focus on the basics. I'm going to talk about the definition of batch arguments. And I'm going to focus on one important application, how to construct SNARGs for P. Okay? And I hope that by looking at this application, we're going to develop some intuition for how to use BARGs more generally, what makes BARGs so useful in many other applications. And if you want to hear about more recent stuff, then next talk by Zhang is going to be about that. And also tomorrow, Surya is giving a talk. OK, let's get started. OK, so SNARGs, just in case this is the first talk you're attending this week. What are SNARGs? So I'll just remind you. So SNARGs for NP, we fix some NP language. And a SNARG for L is just a non-interactive proof in the CRS model. So the prover and verifier both get the CRS. They both get the instance X. The prover also gets a witness. And it produced this proof. It's just one message. So this proof is computationally sound. It's what we call an argument system. There's also a security parameter. I'm not writing this explicitly on the slides, but this parameter controls the soundness error, and it affects the efficiency. Everything here grows with the security parameter. And in terms of efficiency, we want the proof to be succinct. So at least the proof should be shorter than the witness. And ideally, the proof should not even grow with the witness at all. It should just be some fixed polynomial in the security parameter. Now, in addition to short proofs, we also want very efficient verification. We want that the running time of the verifier is maybe ideally it should be quasi-linear in the instance, in the length of the instance. So these SNARKs, they're not just interesting for NP languages. They're also useful for languages in P. So here the computation is deterministic. There is no witness. The verifier could, if we wanted to run the computation on its own, but still it should be faster to verify a proof than to re-execute the computation. OK, great. So we have these two notions of SNARGs, SNARGs for P, SNARGs for NP. And our entire story today is taking place in the gap between these two notions. Okay. So let me start by just saying what we know. So what do we know about SNARGs for NP? Here we have this very important barrier by Gentry and Wicks. And roughly what it says is that if your language is hard, then you don't expect very short proof. So say that it takes that you cannot in 2 to the L time distinguish yes instances from no instances, then you don't expect proofs of length much less than L. Specifically, if your language is exponentially hard, then you don't expect proofs to be shorter than the witness. There's a lot of caveats here. This holds only for adaptive soundness and with respect to black box reductions to efficiently falsifiable assumptions. And really, if you're willing to make kind of strong sub-exponential assumptions, then we can get around this barrier. I'm going to talk about this more in a few slides, but Mostly today, we're going to focus on polynomial assumptions, efficient security reductions. And in this regime, based on our current understanding, this is a real barrier. OK, so moving on to SNARKs for P. Here, we actually have some recent positive results. OK, we can construct SNARKs for P from different standard assumptions like LWE and other assumptions. And what I want to tell you about today is how do we get these positive results, and also how can we push these results as much as possible towards SNARKs for NP. Okay, and the way we're going to do that is using this notion of batch arguments, or BARGs. So what are BARGs? So BARGs are basically a weak form of SNARKs. In a SNARK, we prove one statement. In a BARG, we prove a conjunction of k NP statements. And we're only asking for succinctness, for efficiency, to kick in when the number of statements is pretty large. Okay, so we allow the proof length to grow polynomially with n, with the size of one of the statements. But it should not grow with the number of statements, with k. Okay? So for example, if k equals 1, this would be trivial. You can just send the witness. But when k is large, you're getting something non-trivial. You're proving many statements, and you're only paying for one of them.
So will everything change significantly if you swap n and poly? So the time will be n times poly k? Poly of n. So if n is outside the poly, is it? I mean, that seems to be the useful one.
No, you can get.
Use this poly?
No, you can get this.
Oh, you'll get it. So you're not going to cheat.
No, so the correct answer is not n. It's actually m, the length of the witness, maybe. But you cannot do better than the length of the witness, but it's polynomial in the length of the instance. But so why is it actually the length of the witness? Let's think about it for a second. So we can see that this is really matching the Gentry-Ricks bound, right? So how hard is it to decide this conjunction? You can always do brute force search. And you don't have to brute force over all the witnesses together. You can kind of brute force over one witness at a time because it's a conjunction, right? So every witness is of size poly n, or whatever the size of the witness is. So it's 2 to the poly n times k, linear in k. Okay, so if you take the logarithm of this, you get exactly that. We're not expecting the proofs to be shorter than poly n and logarithmic in k. Okay, so but this is okay. This is exactly the length that we're asking for. So we can see that BARGs are really kind of like a weaker notion than full-fledged SNARKs for NP. But we'll see that if we adopt the right definitions, then we can show that BARGs imply SNARKs for P. Okay, so they're somewhere in the middle. This is how we get all these positive results. But actually, BARGs can do a lot more. They can kind of we can kind of use them to get all kinds of applications that lie in this gap between P and NP. All kinds of applications that previously we can only achieve based on SNARKs with a K, SNARKs with knowledge soundness for NP, things that previously we can only do based on heuristics, and now we can do them based on standard assumptions. Okay, so let me kind of draw a rough picture of what we know. We have batch arguments. First of all, we know of constructions. We have a construction from standard assumptions, either LWE or the Dillon assumptions in bilinear groups, or from sub-exponential DDH. So there's a lot of citations on this slide. I didn't have space to write all the names, but all the names appear in the last slide if you're interested. I'm not going to talk too much about construction today. Let me just say one thing about them. So even though they were all discovered around the same time, these constructions are actually very different from each other. So the construction from LWE and from DDH, they're relying on this notion that Alex told us about of correlation interactability, and they have a short CRS. In contrast, this construction from pairing does not rely on correlation interactability. It has a long CRS. And if you're willing to use the BARG in a non-black box way, you can bootstrap this and get a short CRS in a generic way. But something different is going on here. Okay, so we're not going to talk about constructions today. We're mainly going to focus on applications. So the first application I already mentioned is to getting SNARGs for P. And interestingly here, we also have some sort of partial implication in the other direction. And that's a little surprising because batch arguments are proof systems for NP. We can show that some strong notion of RAM SNARGs for deterministic computation is actually equivalent to batch arguments. So I find that interesting. So I'm going to talk about this application today, and there's a lot of other applications that I'm not going to talk about today. So we can get stronger proof systems. For example, we can have SNARGs for RAM programs. I'm going to mention this today. SNARGs for very interesting subclasses of NP. This is going to be the next talk. We can get incrementally verifiable computation. Benedict talked about this, and we're going to see it tomorrow. And we can also get applications that are not kind of directly related to proof systems. We can get stronger types of aggregated signatures, better rate for NISX, and stronger security for private information retrieval and for FHE. Okay, so really a wide range of applications.
I know you say you didn't too much, but is this equivalence unconditional, or do you need an assumption?
There are other assumptions, yeah. It's not, I wouldn't call it an equivalence, but it's kind of a moral.
Okay.
You need other primitives that we can construct for more assumptions than just BARGs. So one thing that all these applications have in common is that we can achieve them if we're willing to assume SNARKs with knowledge soundness for NP. Okay, so the downside here, of course, is that currently we don't know how to construct SNARKs from any falsifiable assumption. Okay, so really the interesting question, I think, in this area is, I think a really important open question here is to try and understand in which type of applications we can replace SNARKs or SNARGs for NP with BARGs. Okay, so we don't have a really good understanding here. We have a lot of example. Our set of example is expanding, but it will be great to get a better understanding here. Ideally, we can even use BARGs together with other standard assumption to maybe construct SNARKs for NP. This would be a great result.
So if you replace BARG G with a K, is this notion much harder? BARG?
BARG. No, so the notion of BARG is that we're actually constructing and using in all these applications is, in some sense, a BARG. Okay, so somewhere BARG. So the type of knowledge extraction that we get from these BARGs is going to be kind of the main topic of this talk. This is what makes these object interesting, and we don't have a special letter for this, but there is some baked-in knowledge extraction there. It's just not the type of extraction that we're used to in SNARKs. Okay, so I'm going to talk about this. Okay. More questions?
BARG to the C.
Okay, so one last slide on background before I move on to the technical stuff. So I mentioned that from BARGs we can construct SNARGs for P, and I want to compare this to another construction of SNARGs, this time for NP, based on indistinguishability obfuscation. So the reason that, based on I/O, we can get SNARGs for NP, the reason that we can kind of cross the Gentry-Wicks bound is because this construction is based on a sub-exponential assumption, and the reduction here is running in exponential time, exponential in the witness length. Okay, so as a result of this, also the length of the CRS in this construction is as long as the witness. Okay? And the SNARKs that we're going to see today are very different. They have an efficient reduction. They have a short CRS. So there's already some significant difference. But there's another important difference that I want to highlight. And this difference has to do with the proof techniques. So in the SNARKs that we construct from I/O, in the proof is kind of soundness only. Okay, what does it mean? It means that we don't have any sort of knowledge extraction. From the proof, you don't learn anything about the witness. Okay, it's kind of zero knowledge. And in contrast, in our SNARGs, even though they're for deterministic computation, there's no witness, we're going to rely heavily on knowledge extraction. Okay, it's not going to be the regular knowledge extraction. It's going to be something that I call partial knowledge extraction. I'm going to spend some time explaining what it is, because I think this is kind of the main thing that makes these BARGs useful, the main reason that we can use them to replace SNARGs in some applications. Okay, so next what I want to do is I want to define this notion of BARGs, and I want to use them to construct SNARGs for P. And the way these two things were developed was kind of very interconnected. So I apologize in advance. I'm going to kind of jump back and forth between the definition and the application, and I hope you can keep track. Okay, so just so we're all on the same page, let me describe a little bit more precisely the syntax that we have for our BARGs. So again, we have a CRS. The CRS is going to the prover and the verifier. And now the prover is taking as input a sequence of k NP statements, x1 for xk, together with their witnesses. So all the statements must be true. Okay? And it creates a proof. And the verifier, it's also given the instances, x1 for xk, and the proof, and it can verify. Okay? We said that the proof needs to be relatively short. It can grow with the length of one instance, but not with the number of instances. And in terms of verification time, so we can't really hope for verification time to be sublinear in k, right? The verifier at least needs to read all the instances. But it turns out that if your instances are kind of very uniform, if you can compress them in some sense, then you can get verification to be sublinear in k. Okay, so this is going to be important for us in a bit, so I'm going to say a little bit more about this in a few slides. Okay, questions? Okay. So the next thing we need to do is to define soundness. And actually, the soundness definitions for BARGs that we're going to use is kind of tricky. So I'm not going to just dump it on you all at once. I'm going to build it up in a few stages. So let me start with just the simplest vanilla soundness definitions that I can think about. And we'll try to use it. We'll see how far we get. And then we'll revisit this definition. And we'll make it a little bit more interesting. Okay. So how would we define soundness? So we say that for every efficient adversary, P star wins the following soundness game with negligible probability. So P star is choosing a sequence of instances. We give it a random CRS. And then it needs to give us a proof. And the adversary wins if this proof is accepting. But at least one of the statements is false. Not all the statements are true. So this is what we call a non-adaptive or selective security. You can also think about a slightly stronger notion of security, adaptive security. Here we want security even if the adversary can choose the instances as a function of the CRS after seeing the CRS. So if you want adaptive security game, you just switch the order of these messages. First the adversary gets the CRS, then it chooses the instances and the proof together. Okay, great. So this will be our notion of soundness for now. Okay, so now that we have some notion of BARGs on the table, let's try to use it to construct SNARKs for P. And we'll see how far we get. Okay. So let's fix some language in L in P. And M is a deterministic polynomial time Turing machine that decides this language. Okay, so if you want to decide if X is in the language or not, you just need to run this machine. And the execution of this machine looks something like this. It's like we start from the initial configuration, which is just the input. And in every step, we update this configuration. So we have a sequence of configurations from C0 to Ct. T is a polynomial. It's the running time of the computation. Okay. So we're also going to denote by S the space of the computation, the size of one configuration. And for now, just for simplicity, I'm going to assume that S is small. The space is small. This means that I'm allowing my proof to grow with the space, but I still don't want the proofs to grow with the time. Okay, so later, we'll see how to get rid of this assumption, how to support also computations with large space. Okay, so what's the idea? We want to construct a proof for this big computation, no? And we want to use BARGs. So what we can do is we can take this big computation, break it up into many, many small statements, and then just use a BARG to prove all of these statements together. Right? So one way to do it is to prove that M of X is accepting. It's sufficient to prove that the conjunction of the following statements. First of all, the first configuration is equal to the input. The last configuration is accepting. And for every pair of consecutive configurations, Ci-1, Ci, M really transitions from one to the other. Right? If you prove this conjunction, you prove that M is accepting. So maybe a naive idea would just to BARG all these statements together and send it to the verifier. Okay, so you could do that. The problem is that the verifier can't really check this BARG, right? The verifier, in order to check the BARG, it needs to know all the statements, right? And in this case, our statements are just defined by the sequence of configurations. So in order to verify the statements, the verifier needs to itself compute all the configurations, needs to run the entire computation we're not going to get anything efficient here. So what's the idea to fix this? The idea is that we're going to kind of push this configurations from the statements to the witnesses. The verifier doesn't need to know the witnesses, just the statements. So we're going to simplify the statements and push the configurations to the witness. So how does this work? So we're again going to compute all the configurations, and now we're going to use a hash function to compute a hash tree over this entire tableau. Okay? And now, in order to prove that m of x is accepting, it's sufficient to prove this conjunction of statement y1 through yt, and these statements will be defined just in terms of the root of this hash tree. Okay? So the if statement, yi, is as follows. The if statement is true if there exists, the witness is these two configurations, ci-1 and ci. If there exists a pair of configurations that are, on the one hand, consistent with the root, we can have a local opening for them. And on the other hand, they're consistent with the computation of m. M really transitions from one to the other. Okay, so the witness contains these configurations and their local openings. Okay? Of course, we again need to check that in the first statement, the initial configuration really contains the input. And when we're checking the last statement, we're going to explicitly check that the last configuration is accepted. Okay, so these are going to be our statements. Okay.
Are you still in P if you have to then have a witness for the premix of the hash?
Yeah, part of the witness. So the witness contains the two configurations and the local openings with respect to this hash.
He's using a BARG for NP, so he's
okay. Yeah. Okay. So using this notation, let's see how our protocol looks like. So the prover is going to first run the computation, get all the configurations, compute a hash tree over them. This hash tree, the root of the hash tree will define these yi statements. And then we're going to BARG all these statements. Okay? Then the prover sends to the verifier the root of the hash tree. Okay? The verifier doesn't know the root. It depends on the computation. So we send the verifier the root together with the BARG proof. The verifier can use the root to define all these statements and verify the BARG. So in terms of proof size, we're good. The root is very short, and this BARG proof is polynomial in the size of the statement. The statement is it's like polynomial in the size of one configuration, polynomial in S. We said that S is small, so we're fine with that. Okay. The problem here, of course, is the running time of the verifier. So if you do things naively, you still need to compute all these T statements, right? So the running time of the verifier is going to grow with the running time of the machine. But here we're going to exploit the fact that all of these statements are actually computed from the same hash root. So let me define a little bit more precisely the property that we want from the BARG. This is something that we call index BARG.
Omer?
Yeah.
So from what we've seen so far, like it's not clear why the underlying machine needs to be deterministic as opposed to not deterministic. Right. Like it's not syntactically would be fine.
Right, and it's going to come up.
Okay.
When we start talking about security, you'll see. Okay. So, so we need something like an index BARG. What is an index BARG? It looks exactly like a BARG, but now if the statements y1 through yk are uniform, then we can do something better. What is uniform? It means that there exists one string y that that can be used to generate all these other statements. So every statement yi, we can compute it using just y and the index I.
The computation taking into account that.
Yeah, as long as it's polynomial time, I'm not paying for
No,
it.
but small, obviously. I mean, the whole point is to compress the polynomial.
But actually, nothing is going to grow with this computation, this purple computation. Okay, so if you have such uniform statements, then the verifier just need to know kind of the explanation for all the statements. And now the running time of the verifier will only grow with the size of y. Other than that, it's not going to grow with the number of instances at all. Okay, so going back to our protocol, we can see that all these yi statements can be computed from the root of the hash tree. Okay, so we can really get verification time that is sublinear in the number of statements, which is t, the running time of the computation. So this is our protocol. And now we need to talk about soundness. This is where things are going to get a little more interesting.
Can it be clear to us how you do it, or
how you do what?
This index bar.
This index barg. No, so I'm going to keep introducing properties for the barg. You know, these were syntactical properties or efficiency properties, and I'm also going to introduce stronger and stronger soundness properties. Okay, and I'm not going to explain how we construct them, but I will try to, only introduce properties that we do know how to construct, not cheat.
But at the end of the day, you're saying we don't know how to go from BARGs to SNARKs for P. It's only for super special kind of BARGs, right? Or is the statement generically true?
So this super special type of BARGs, all of our constructions satisfy it, and this will be my regular notion of BARG. Super special. No, I mean, people have constructed and defined weaker BARGs, but I think they're really less useful. So this is the notion I want to focus on. OK, so let's try to talk about soundness and see what happens. So this is our protocol. And if you kind of try to naively prove the soundness of this protocol, it looks like to prove that it's sound, you need to rely on very strong soundness properties from the underlying BARG. In fact, too strong. Okay. So let's see why. So first of all, you need the underlying BARG to be adaptively sound. Why is that? You need that the BARG is secure even if the prover chooses the statement as a function of the CRS. So let's see why. So in this protocol, the statements are defined by the root of the hash tree, right? And the root of the hash tree is sent together with the proof. So if our prover, there's nothing preventing a cheating prover from selecting this root as a function of the CRS. Right? So if we don't have adaptive soundness, we're kind of dead in the water. So we need adaptive soundness. That's the only thing we need. We also need some sort of knowledge soundness. So it's not enough that to prove that all these Y statements are true. We actually need to, in the reduction, we need to be able to extract the witnesses for this. Why is that? So remember, our construction is using also a hash tree. Right? And if we have an adversary that can find collisions in this hash tree, can open the same configuration in two different ways, then this adversary can definitely break soundness. Okay? So we want to reduce this type of adversary to finding a collision. But in order to do that, we have to extract the witnesses for these statements. This is where the authentication paths are actually found. So in order to find a collision, we need to actually find the witnesses for these statements. Okay, so it seems like without adaptive soundness and knowledge soundness, we're kind of stuck. Okay, so now for the bad news. So the BARGs that we know how to construct are selectively sound. They're not adaptively sound. Constructing BARGs with adaptive soundness is, for polynomial assumptions, it's an open question. Now, if you're asking for both adaptive soundness and knowledge soundness at the same time, this is really taking things too far. So we know that these two properties together already implies full-fledged SNARKs for NP. We have very strong barriers here. So I'm not going to explain why that is, but just the idea. So basically, the idea is that something that is very similar to the construction we just sketched, as Ale observed, the same thing will work even for non-deterministic computation. Okay, so if you have these two properties, the construction that I sketched will be can also be modified to prove all of NP. Okay, so in some sense, these two properties are too strong. Okay.
What exactly is meant by SNARKs for NP? Like what auxiliary information? I mean, these contention results. What exactly? Is there a commonly agreed notion of what SNARKs for NP precisely mean?
I mean, if the extractor is like universal or non-universal auxiliary input or stuff.
I mean, there are these contention results, right, that show that strong.
That's what I mean when I say we have barriers. Okay, so I don't want to get into the precise definition, but we don't expect to build any of this based on standard assumption or at all.
Okay.
So why is this not a problem for SNARGs for P?
Okay, so we need to find kind of, so what we need to do now is to find so I didn't show the analysis, but this would kind of be, the analysis that you would expect. What we're going to do now is we're going to go back and revisit the definition of soundness for BARGs. We're going to find a weaker definition. So we need a definition, kind of a Goldilocks definition, that it's not too strong that it gives us full-fledged SNARKs for NP, but it's strong enough that we can use it to analyze the security of our protocol using the fact that it's a deterministic computation. This is exactly what we're doing. Okay, so back to the definition. The definition that we're really going to work with, the definition that we need from our BARGs, is called somewhere soundness. It's coming from this beautiful work by CJJ. So in somewhere soundness, we're thinking about an adaptive adversary, but we're kind of relaxing the soundness requirement. So in regular soundness, we kind of want all the statement x1 for xk to be true simultaneously. In somewhere soundness, we're kind of thinking for every index I, we have some hybrid experiment, indistinguishable experiment, where we're guaranteed that the if statement is correct, but there is no one experiment where all the statements have to be correct. So let me explain a bit more precisely how this works. So first of all, syntactically, we're going to have this alternative way of sampling CRSs. There is an algorithm gen star. You give it the index, and it generates a CRS that is programmed with the index I inside of it. So this programmed CRS is going to be indistinguishable from the normal CRS. And under this programmed CRS, we are guaranteed that the if statement is correct, but we have no guarantee for any other statement. So a bit more formally, the two properties, somewhere soundness requires two properties. First of all, we want CRS indistinguishability. For every I, we want the normal CRS sampled by gen and the programmed CRS on I to be indistinguishable from each other. Okay? And the second property is somewhere soundness. It says that for every index I, we let our adversary play the following security game. So first we give the adversary a programmed CRS on I, and then the adversary outputs a sequence of instances and a proof. So this is an adaptive adversary. Okay? And we say that the adversary is winning if the proof is accepting, but the statement xi is false. So before, we just wanted some statement to be false. Now we're just focusing only on the statement xi. Okay, so this is somewhere soundness. So just to get some feel for this definition, let me give an example where it kind of separates somewhere soundness from full soundness. Okay, let's see why somewhere soundness is really weaker than full soundness.
And is I known ahead of time, the position?
This is for every I. This holds. So you always get soundness for the I that you programmed in the CRS. Okay. So let's try to understand what's the tension between somewhere soundness and full soundness. So let's say that I have some cheating prover P star that is able to do the following thing. We give this cheating prover a CRS programmed on index 1, and it gives us back two statements, k equals 2. The first statement x1 is true, and the second statement x2 is false. And it gives us a correct proof, an accepting proof. Now the same adversary, if you give it a CRS that's programmed on index 2, it's giving you the first statement false, the second statement true. Okay, and an accepting proof. So clearly, we don't have soundness here. No matter what we put in the CRS, at least one of our statements is going to be false. There's always a false statement. Okay? But what I'm arguing is that this type of cheating prover is not ruled out by somewhere soundness. Okay, this could still be somewhere sound. Why? We program the index 1, we get a true statement in the first, and we program the index 2, the second statement is true. Okay, now we also know that these CRSs need to be indistinguishable from each other. This means that also the instances that the adversary will sample for us are also going to be indistinguishable from each other. But there's no contradiction here. You know, if we're working with NP languages, if your language is hard, it's very possible that you have a true statement x1 that is indistinguishable from a false statement x1 prime. Okay, so there's really no contradiction to somewhere soundness. So intuitively, what is going on in this example? So in this example, the adversary is kind of mauling the CRS. Okay, so it doesn't know what's programmed inside the CRS, but it picks its statement somehow dependent on the CRS in a way that it matches. And the adversary itself does not know which one of the statements that it chose is true and which one is false. Okay, it's a mauling attack. Okay, so this is why somewhere soundness seems weaker than full soundness. And we're going to see how to use it to prove the correctness of our protocol for deterministic computations.
So check somewhere is sandwiched between non-adaptive and adaptive.
so the way I define somewhere, it's just adaptive. It's considered an adaptive adversary. Okay, if you have somewhere soundness, the way I define it, you can show that in the static, if you have a static adversary that doesn't change the statement, always outputs the same statement in both cases, then all the statements have to be true. So actually, somewhere soundness in the way we define it with an adaptive adversary implies full soundness for static adversaries. But I'm not going to use this today. But it is soundness.
And Omer, so here, this is just an informal statement. You're not making.
Yeah. This is just an intuition. Yeah, but I can give you an example like this. You know, think about X state X1 as being the statement the CRS is programmed on 1, and this statement is the CRS programmed on 2. So you get exactly this.
CRS could be X1, X2, right? I mean, it could be identity function. CRS is equal to X1, X2, and then the statement is identity function, right?
No. I'm not sure.
No, I'm saying the CRS could be, let's say, the honest CRS is 2 true statements, doesn't matter what it's good for. Dishonest CRS would be false true and true false, right? So it's kind of identity function.
It's not useful. Like
it's not useful, but I'm saying that's his point.
Okay, I hope this gives you intuition, but not confuse us too much. Okay, so so as I mentioned before, just soundness is not enough. We need some sort of knowledge extraction. So let me just explain how does knowledge extraction look like in the setting of somewhere soundness. Okay, so if we call this somewhere knowledge soundness naturally. So syntactically, when we generate the programmed CRS, we're also going to sample it together with some trapdoor. And this trapdoor is going to, this is what we're going to use for extraction. Okay. So now the definition looks exactly like it did in the case of soundness. Let me just highlight what is the difference. So again, the key in this CRS indistinguishability is the same. The CRS is indistinguishable from the programmed CRS. Note that this only holds if you don't know the trapdoor. If you know the trapdoor, if you can extract the witness, then obviously you can distinguish. Okay, but as long as you don't know the trapdoor, you have indistinguishability. And now we have somewhere extraction. So there exists some extractor E, such that if there is any cheating prover that wins that plays exactly the same game as before, not only that the if statement is guaranteed to be true, we can actually extract a witness for the if statement. So we have an extractor, we give it the trapdoor and the proof, and it will extract for us some witness for the statement xi. Okay, so this is a stronger property. So note that here our extractor is not getting the code of the adversary. It's not even getting black box access to the adversary. All the extractor is getting is just the trapdoor, and then it extracts the witness directly from the proof. Okay, so this is kind of not the type of knowledge extraction we're used to in the context of SNARGs. So let me say a few more words about this. Let me do a comparison between the type of extractor we have from BARGs and for SNARKs. So as I said, in BARGs, we extract directly from the proof. In SNARKs, for NP, we usually extract either from the code of the adversary or from the queries of the adversary if we're working in some idealized model. And intuitively, the reason for this is that in the setting of BARGs, we're just trying to extract one witness, right? We're not trying to extract all the witnesses. So essentially, we're extracting something that is shorter than our proof. This means that we can hope to extract it directly from the proof. In contrast, in SNARGs, we want to extract the entire big witness. It's much larger than the proof. So there's really no hope to extract it just from the proof. You have to extract it from somewhere else, maybe the code of the adversary. Now, the problem is that we don't really have techniques for extracting things from the code of the adversary. So this is where we rely on heuristics, so knowledge assumptions, idealized models, and so on. In the context of BARGs, we don't need to do that. So last important difference, this type of extraction actually makes this notion of BARG into a public key notion. We can show that this notion of BARG with this type of extraction implies private information retrieval, public key encryption, CRHs. And in contrast, for SNARKs, we don't know any such implications. Okay, so actually, because of this extraction, the notions of BARGs and SNARKs are incomparable to each other. Okay?
I don't know if it's a problem of BARG. Like brothers Rosty Sahai or Grot Sahai use similar techniques. Like
I didn't say it's a problem. I think it's a good thing. But all of our constructions are using public key.
It's the succinctness, though. I don't think it's a part of batching, I think. I think it's the succinctness that makes this distinction, not necessarily the B part.
I agree. I think that the key to this thing is that what we're extracting is shorter than the proof. So we can extract it directly from the proof, just like decryption. So, yeah.
Is there something tight in the sense that if I can extract, as soon as I can extract a little bit more than the proof length, then I get SNARK? Or is it too much to?
I think there is. I think there's a. I'm guessing that you can do it, and I think this was written.
Sorry, I didn't catch the difference. You're saying because is it because the BARG has a trapdoor attached to it versus the SNARK just says there exists an extractor? That's the difference that gives you the...
So in some sense, the way we define the extractor here, it's kind of decrypting the witness from the proof. We kind of think about the proof as an encryption of the witness, and the CRS is an encryption of the index. So you can think about the whole thing as like a big PIR protocol. Okay, and here, the extraction, we don't decrypt the witness from the proof. We actually find it in the code of the adversary. Okay, so it doesn't imply anything. Okay. So let me remind you of the protocol. So this is going to be the notion that we're actually going to use. Now we're ready to, we have everything we need to analyze the security of our protocol. So let me remind you what the protocol is. The prover computes all the configuration. It computes the hash tree. And then it sends the hash root together with the BARG for all these statements. And this was our statement. Okay. So we want to prove that this is sound. Actually, this protocol, the way it's written here, it's not quite sound yet. We need to change one more thing. But let's start with the soundness proof, and let's see where the issue is. We're going to get there in just a couple of slides. So soundness. So let's say that there is some cheating prover that breaks the soundness of this SNARG. So we give it a CRS. This is just the CRS for the BARG. And it gives us some input X and a proof that consists of a root and a BARG proof. Okay, and we know that the adversary is winning because if the BARG proof is accepting, but the machine is rejecting, M of X is rejecting. Okay, and let's say that this is happening with probability 1, just for simplicity. Okay. So now what we can do is we can move to an indistinguishable experiment where we give the prover a programmed CRS on some index I. Okay, and the prover cannot distinguish, so he will still win the security game with probability very close to 1, right? Okay, good. So let's see what happens when we give this prover a CRS that is programmed on the first index, on index 1. So the prover is going to give us some X and some proof. And the first thing we're going to do in the reduction is we're going to run our machine on the input X. And we're going to compute all the correct configurations of the computation by ourselves. So we call these are the green configurations here, C0x to CTX. So we know that the machine rejects. This means that the final configuration, the correct configuration of the T step is rejecting, right? We also know that the verifier accepts the BARG proof, which means that we can extract from this proof. We extract a witness for the first statement. This is what we programmed. So how does the witness for the first statement look like? It's just a pair of configurations, right? So what can we say about these configurations? We know that this is a valid witness. And we explicitly check that the first configuration contains the input. So the first configuration has to be correct. We're also checking that the machine transitions from C0 to C1. So this a deterministic machine. This means that the second configuration, the C1, also has to be correct. When I say correct, it means it's equal to the green configuration. Okay, so we got that these two configurations are correct. That's great. Now the idea of the proof is that we want to keep extracting all the rest of the computation, and we want to maintain the invariant that everything we extract is always correct. Okay, so let's see what happens when we take just one more step. Okay, things start to go wrong. So now we're going to program the CRS on index 2. Okay, and the CRS changed, so the prover can give us a different statement, x prime. And we can again run the computation on x prime, get all these correct configurations, and we can also extract a witness from the proof. This time the witness contains a pair of configurations, C1 prime, C2 prime. Okay? And what do we know? We know that this is a valid witness. So if C1 is correct, C2 has to be correct as well. Okay? The problem is that now we really have no way of arguing that C1 is correct. So before we were extracting C0, we used it to argue that C1 is correct. Now we cannot do it anymore. So one thing that is tempting to do is to say, look, this C1 prime is indistinguishable from the C1 that we had in the previous experiment, right? Because we just changed the CRS. We have CRS indistinguishability. So if it was correct before, it should be correct now. Okay, what's the problem with this argument? Right. So the problem is that CRS indistinguishability only holds if you don't know the trapdoor. But how did we compute these configurations? We extracted them using the trapdoor. Okay, so things that you extract, you cannot argue that they're indistinguishable. Okay, so this is not going to work. So we need to go back to our protocol and make one last change. It's a very minor change, but significant. So instead of having one BARG, we're just going to have two BARGs. Okay, we're going to trust me, we're going to have two BARGs. Okay. So we're going to have two independent CRSs. They each
it's indistinguishable whether they're there or not.
Okay, don't move. We have two CRSs, CRS and CRS tilde, and we're going to have one root. Okay, for the same root, we're going to just prove all the statements twice. We're going to send two proofs, one under the first CRS, one under the other CRS. Intuitively, why this is a good idea? Because it allows us to program and extract from each one of these proofs independently. Okay, we'll see that this solves our problem. So this is our final protocol. Let's analyze soundness. Okay, so for soundness, we're going to start by programming 1 in the first CRS and 2 in the second CRS. Okay, and we again get some X. We compute the correct configurations, and we extract both a witness from the first proof and from the second proof. So we get these two pairs of configurations. Okay, so we know that the first pair, because this is a valid witness, we know that C0 has to be correct and C1 has to be correct. And we know that the second witness is good, so we know that if C1 tilde is correct, then also C2 tilde is correct. And finally, because of collision resistance, we can argue that C1 and C1 tilde are equal to each other. Okay, why? Because we're extracting witnesses. We're extracting local openings of C1 and C1 tilde with respect to the same root. Okay, so because we're extracting them with the same root, with respect to the same root, they're going to be equal. Otherwise, we find a collision. Okay. So this correct implies that this correct, they're equal, and this correct implies this correct. We get that everything is correct. Okay, all the first three configurations are correct. Now what happens when you try to make a step? Okay, so how does our step look like now? We're going to keep the second CRS programmed on 2. And we're just going to change the first CRS. What are we going to program there? What's after 2? Okay, 3. So now, again, we get an instance. We write the correct configurations. We can keep extracting from the second proof, okay, these configurations, C1 tilde, C2 tilde. And note that in order to extract these configurations, we just used the trapdoor for the second CRS, right? We didn't use the trapdoor for the first CRS. And since we only changed the first CRS, now we can use the CRS indistinguishability for the first CRS and argue that these extracted configurations are indistinguishable in these two experiments. So if they were correct before, they have to be correct now. If they stop being correct, then we can use this to break the CRS indistinguishability of the first CRS. Okay, so now we have two correct configurations. Now we can extract from the first proof, and we get another pair of configurations. And just like before, we know that this is a valid witness. So if C2 is correct, then C3 is correct. And because of collision resistant, we have equality here between these two configurations at time 2. So this means that C3 has to be correct as well. Okay, so I hope you follow this. Yeah.
I thought we were for the SNARG. I thought we were arguing selective security, but here P star is choosing X after the CRS.
Our SNARG is going to be adaptively
secure. It'll be adaptively secure.
Yeah, it's going to be for P, but adaptively secure.
Okay.
The reason is that you can always compute these correct configurations. You can give me whatever X you want. I can compute this.
I guess for the yeah, okay, I see. But so it doesn't make it easier for it to be selectively secure.
Slightly easier. There were like 5 years where we only could do selective, but at some point.
But you still have this problem even with selective security, like this
yeah, most of the proof is going to be the same for selective. Okay. So we're going to keep doing this lockstep until we get to the final pair of configurations. By induction, we can argue that this last configuration has to be correct. The correct configuration is 0, is rejecting, because the computation is rejecting. On the other hand, we know that this is a valid witness, and we explicitly check that the final configuration is always accepting. So this configuration has to be rejecting, it has to be accepting. This is where we get the contradiction. Okay, so we're pretty much done with the soundness proof. Any questions about this?
I just got confused a little bit. So if you change the CRS, the statement X always changes?
Always changes.
So why is it useful? I mean, you're trying to...
Because all I care about is whether these configurations are correct or not. What is correct? I compare it to the correct configuration that I computed from the X that I got. Okay, so the X changes, but being correct has not changed.
Even though the X changes, you can trace it and actually backwards for the same X, kind of?
Whatever X you give me, I'm going to define all the correct configurations, and then I'm going to ask, is the configuration at the ith location correct or not? Okay, you can give me something else, but the predicate of being correct, the testable predicate, is going to remain the same.
But also, like, you only change the, I mean, does the root change? Oh, yeah, you can. Okay.
When you were arguing like the CRS, like indistinguishable, like oh, like these two CRS, like the first CRS is indistinguishable, so we can like assume that C1 and C2 are like continue to stay correct. Isn't that like a problem because you did have the trap, like to deduce that C1 and C2 were correct in the beginning, you had the trapdoor for the first CRS, right?
No, I can do, you think about an experiment where I get a first CRS, I have no trapdoor for it, I don't know where it came from, and I just extract from the second CRS and test whether it's correct or not. So you give me, you change the first CRS, I'm not gonna know. So I don't expect to see any change. Okay, so the predicate that you were testing is only using the second CRS, the second trapdoor, not the first trapdoor. Okay, great. So the last thing I want to do very briefly is to talk about large configurations. So far, we assumed that the space is small. What if the configurations are large? Okay, so the way we're going to deal with it is again by hashing. So this time we're going to first hash each configuration individually. Okay, so for each configuration, we're going to compute a hash tree over this configuration, and we're going to keep the root of this hash tree. So now instead of sequence of configuration, we have a sequence of roots. And whatever we did before with the configurations, we're going to do with the roots of these configurations. So the way it looks like that we write the roots of the configurations, they're always small. We compute a hash tree over that. Okay, and now we're going to say that m of x is equal to 1. We're going to break it down into a sequence of statements. And these statements are very similar to before, just a minor change. So we're going to prove that for every I, there exist roots, di minus 1 and di, that are consistent with this big root. They have local openings. And also they're consistent with m. So you can open them to full configurations that really m transition from one to another. So this is not something that you can test by yourself. You know, I give you two hashed configurations. You can't check if they're consistent, but you can prove that they're consistent, right? The computation is local. It's only changing a few bits of the configuration. So I can give you local opening for all these bits, all these locations, and then you can check that these configurations are really consistent with each other. Okay, so this is how we're going to prove this part. And also, of course, when you check the first and last configuration, instead of comparing them to x and to 1, compare them to the hash of x and the hash of 1. Okay, because everything is hashed. Okay, so just to see how this change affects the soundness proof. Okay, so just for this, I'm going to just focus on the first index, and I'm going to ignore the second CRS altogether. This is just to give you a flavor of what's going to change. So first of all, instead of computing the correct, we're still going to compute the correct configurations, and then using the correct configurations, we're going to compute the correct roots of the configurations. From there on, everything is the same. And we need to argue that if D1 is correct, D0 is correct, then D1 is also correct. So before this was unconditional. Now, if we get D1 that is correct, but D0 that is correct, but D1 that it's incorrect, we can kind of look at the authentication paths for the correct configurations and compare them, and this will give us a hash collision. Okay, so we still can argue that if D0 is correct, then D1 is correct. This is just a computational statement. Okay, so this is roughly what's going on in the proof. Okay, so I'll just say briefly that this idea of hashing down the configurations is very, very useful, especially when you're trying to argue about computations over very large inputs. Okay? So what is the observation here? The observation is that in our protocol, the verifier doesn't actually need to know the input x, right? It's enough that it knows the hash of the input. Why? Because in order to define this first statement, we're just comparing to the hash of x. We're not using x. So this is great. It turns out to be very useful. We call it RAM SNARKs. Okay? When you use RAM SNARKs, you need to be a little bit careful. There's a caveat here. And the caveat is that in the security reduction, we still need to know what x is. Okay? It's not enough that the security reduction knows the hash of x. It needs to know x. Why? Because if you only give me the hash of x, I cannot compute the correct configurations. I actually need to know x to compute all the correct configurations and then hash them. I can't start with a hash and do the computation.
Otherwise, you have a SNARK for NP.
Exactly. We'll see that. So I mean, I don't want to go through the formal security definitions for these objects, but let me just give you some intuitions of how to use this, when it's OK to use RAM SNARKs and when it's not OK. So the first example is going to be kind of a memory delegation. We have a verifier, a client. It has some large memory, all of its emails maybe. It delegates it over to a prover. And now the prover is going to store x. Okay, and in the future, the verifier might want to compute on this x. Okay, so now the verifier can forget x. Okay, it only keeps a hash of x. And at some point in the future, the verifier asks the prover to prove some statement about its emails and check it. Okay, in this case, the verifier doesn't need to download the entire x. It can verify using the hash. Okay, so in this case, we have soundness because our reduction knows x. X was selected by the honest verifier, so the reduction knows x. Okay, now let's try to see an example of how not to use RAM SNARKs. This is what Surya suggested. So in this protocol, we have just one message. The prover is selecting some input. It hashes the input. And it sends to the verifier the hash of the input and a proof that this input makes the machine accept. Okay? So in this case, we don't have soundness. Okay? This protocol is not sound. Why? Because in the security reduction, we have a cheating prover. It gives us some digest, some hash. We have no idea what's the preimage, so we can't run the reduction. Okay? We can't actually compute from this the correct configuration. It's possible that there is no preimage. Okay? So this is consistent with what we know, because if this was sound, we can actually turn this into a SNARK for NP. Okay, so we don't expect this type of things to be secure. Okay, so I have maybe, no, come on. I think maybe at least 10, 45 minutes. In the next 10 minutes, we're going to, I want to change gears a little bit, and I want to take this elaborate proofs that we did, and I want to abstract it a bit. Okay? So I want to take the main components and try to generalize them, because I think this will help us understand how to use BARGs a bit more generally. Okay, in other applications as well.
Another question. For the construction you've shown, we were using just succinctness, not it's a proof succinctness rather than verification succinctness.
We're also using. Yeah, the verification can grow with the size of one instance, but it shouldn't grow with the number of instances.
Why not the number? Because number was bounded. Were you like using
the number of instances was t, was the size of the computation.
Altogether, yes. There was no recursion. Yeah.
But in terms of verifying one instance, you can grow with the NP verification circuit. That's one problem. Okay, so I want to take kind of the main component of this construction and abstract it and look at it more generally. So in the construction, we used a hash function, on top of it a BARG, and this combination seems very powerful. And sometimes we just refer to this construction as hash and BARG. Okay? So I want to analyze the properties of this construction. We have this abstraction of this construction, something called a quasi-argument for NP. So I want to tell you what are the properties here. And for me, at least, thinking about quasi-argument is very convenient because it helps me understand in what type of applications we can use BARGs to replace full-fledged SNARKs for NP. OK, so now instead of proving a deterministic computation, we're going to deal with constraint satisfaction problems. Okay, I'm going to run through it because I'm assuming that you know this. There's a sequence of variables and a sequence of constraints. Okay, and you want to find an assignment for the variables that satisfies all the constraints. The classic example that we all know is the NP-complete problem free sat. Here, the alphabet is just binary, and every constraint is just a disjunction of free literals, just a clause. Okay. So everything I'm going to, for now I'm going to work with free sat. I'm going to, just for concreteness, but everything I'm saying from now holds for general CSPs. So let's try to use hash and barg to prove that a free set instance is satisfiable. Okay? Obviously, we're not going to succeed. We're not going to get SNARKs for NP, but let's see what we get. So both the verifier and prover get the statements, the constraints, and the prover also gets the witness, which is the assignment. Okay? The prover will compute a hash tree over this assignment, and now it's going to compute a barg proof that basically all the constraints over this hashed assignments are satisfied. Okay, so the way this works is that for every constraint, we're going to have a statement that says that if this constraint is over the variables x, alpha, beta, and gamma, then there exists some openings, sigma alpha, sigma beta, sigma gamma, that are consistent with this root, and they satisfy the constraint ci. So for every ci, we're going to have one of these statements, and we're going to prove all of them together in a barg. Okay, so we're going to send the root and the barg proof, and the verifier can check. Okay, so this is, we don't expect this to be sound, right? If this was sound, we get SNARKs for NP. But what kind of soundness do we get from this? It's a good question, probably nothing. So based on our iteration from before, we know that sending just one proof is not a good idea. So instead, we're going to send L proofs. Okay, L is some parameter of our construction. We're going to have L independent CRSs, and we're going to send L proofs with the same root. Okay. And now the big question is, how does the soundness of this construction depend on L? Okay, and the nice thing about this construction is that when you make L larger, you kind of expect better soundness. But in terms of succinct, you pay in succinctness, right? The proofs become grows linearly with L. So I don't have much time, so I'm just going to briefly run through the definition of quasi-argument. The definition of quasi-argument is basically capturing the type of soundness that this protocol satisfies. Okay? So a quasi-argument is weaker than an argument. It's weaker than a SNARK for NP because the soundness property or the knowledge extraction property is weakened. Okay? Instead of full extraction, we have partial extraction. So the way it works is that a protocol is a quasi-argument for free sat. If any prover that makes the verifier accept, we can turn it into an extractor for the assignment. Okay? But this is a local extractor. It's what we call an L-local assignment generator. So what is an L-local assignment generator? So you can choose any small set of variables, at most L variables. And then you can give the extractor the set of variables, and the extractor will sample for you an assignment only for these variables. Okay? So our guarantee is that this extractor samples assignments that are kind of look good. Okay, what does that mean? Very subtle. So what does it mean that they look good? It means that, first of all, they satisfy all the local constraints. Okay, so at least locally, they don't violate any constraints. And the second thing is that we want to guarantee some consistency. So you know what happens when you sample assignments for two sets of variables that are overlapping with each other? So you're not guaranteed that these variables are getting exactly the same values. They can be inconsistencies. But if you restrict yourself to looking at variables in the intersection of these two assignments, you're guaranteed that the distribution of assignments here and here are indistinguishable from each other. This property is called non-signaling. Okay? So if you think about it as an extractor, this is kind of unnatural at first. It's maybe a bit confusing. But actually, we've been thinking about these no-signaling extractors for a while. We have good understanding of what they capture. Okay, so now using this, we can see that our construction really gives us this quasi-argument. Okay, the idea is that if you want to extract on a set S of variables, just program your CRSs, each one of them on a clause that contains these variables, and now extract the values of the assignments just from these variables from each one of these proofs. Okay, and very roughly, we can prove that local consistency of this assignment generator based on the somewhere extraction of the BARG, and based on the CRS indistinguishability of the BARG and the fact that all these CRSs are independent of each other, we can get non-signaling. Okay, I know that this is a little bit fast. Just to, maybe I'll just skip the examples and I'll jump straight into open questions. So I wanted to show you an example how to use a quasi-argument to get, to kind of simplify the proof that we saw so far for SNARK for P. It can dramatically simplify it. We can also use it to get BARGs back. So quasi-arguments and BARGs are actually equivalent to each other. I'm skipping this.
Returning to SNARKs for P, there, through this abstraction, you can really use L equals 2.
Exactly. No, I mean, because if your variables are Boolean, then you need like one for every.
Yeah, but you just use a larger alphabet.
Yeah, you can use a larger alphabet, size 2 to the S in your group.
Okay, so there's like a large alphabet CSP whose to locality kind of
Exactly.
local extractor. Then. Okay.
Exactly. Okay, so let's do some open questions. So first natural open question is in which applications we can replace SNARGs or SNARKs with BARGs. There's a lot of applications that you can think about. I just wanted to highlight one class of applications that I find particularly interesting. So you can, and that's succinct non-interactive secure computation. Okay, so we can build a secure computation that is non-interactive. It's just 2 messages, and it's succinct. So the messages don't grow with the size of the inputs or the size of the computation, just with the size of the output. We can build something like this from fully homomorphic encryption, but it will have it will be semi-honest. It will have selective security, passive security. What if we want malicious security? So far we were able to do that using SNARKs. We just did the general compilation using SNARKs, and that doesn't hurt succinctness. Can we do it based on BARGs, and for which functionalities? Okay, and the reason I think this is an interesting question is because this application really requires knowledge extraction. Okay, SNARGs are not enough here. We need SNARKs. Okay, so in which applications BARGs give us enough knowledge extraction to compile the secure computation? We have some initial results here. We have very simple functionalities, things like private set memberships and stuff like that. But we don't know in general when you can do it from BARGs.
For 2 parties, we do know. For multiple parties, we don't know.
Even for 2 parties, we don't know. In the malicious setting.
Yes, we do know.
Okay, tell me later. We have like minus 2 minutes. Recursive proof composition. This is another application that Benedict told us about that crucially relies on knowledge, right? We do a proof on a proof. And this is useful for IVC, for example, incrementally verifiable computation. So we know how to use BARGs to get incrementally verifiable computation. We still don't know how to generalize this to proof-carrying data, where we want to compose proofs following not just line graphs, but arbitrary DAGs. Okay, this is still open. I think a natural question is to improve the constructions that we have of BARGs. What would make me personally very happy is to have simpler constructions that I can teach you in an hour. By far, the simplest construction is based on pairing, but it's still pretty complicated. So I think we can have better constructions. You can ask for stronger properties. For example, can we get based on bilinear groups as a black box? Can we use them as a black box to get BARGs with a short CRS? We don't know. Okay, so there's all kind of better constructions that you can hope for. Okay, I really have to go. But, questions? So the slide with the citations, you can find the full names here. If you're, so you can look for your name. She knows.
So the reason this doesn't extend to NP is because you need to already know what all the configurations are.
Exactly. Computing I should have said it, but computing the correct configuration is something that you can do for P. Also arguing that if one configuration is correct, the second next is correct, you need to generalize it somehow. But yeah, the main question is, how do you look at the configuration somewhere in the middle and say whether it's correct or not?
So some kind of complexity leveraging tricks don't help here.
They do help, but you don't want to leverage too much so that you grow with the witness. That's the trick. Okay, but we can definitely do some things with leverage. Ada?
Yeah. So about this local assignment generator, so you have these like 2 properties. Both like are one is an indistinguishability, and the other is like local consistency. Which of these properties are usually statistical, and which are usually computational, or like can both be computational?
So the no signaling computational and statistical is a little bit confusing because it becomes stronger when you talk about computational no signaling. But both of these properties have some error, and they're both going to be computational.
Both are computational.
So in general, we can always get like perfect consistency by kind of slightly increasing our no signaling error. We can always push the error to no signaling, but I don't know if that helps.
I mean, in like the usual like hash and bar technique, the consistency comes from the hash, right? So it is computational. The consistency comes.
It also comes from the soundness of the bark. So there's also an error. But
okay.
Yeah, in general, both things can be computational. It's enough for the application. Okay, thanks.